Hi, everybody. Now we're moving on in this half of Unit 11 with chemical equilibrium. And it does relate to how fast reactions proceed, which is what we were talking about in the first half of this unit. Because an equilibrium is established when the forward and the reverse rate of a reversible reaction are equal. First, we're going to take a look at just what do we mean by equilibrium. But by the end of this presentation, you should definitely be able to write an equilibrium expression for a homogeneous or a heterogeneous equilibria. And you should be able to use the equilibrium expression to calculate the value of what's called the KEQ. So at the end of the presentation, you should be able to do those two things. So here's a slide that kind of shows you a reversible reaction. If you have two reactants, A and B, and you pour them together or you place them together in a reaction container, pour them together into a beaker, place them together, and the A and B start bumping into each other and they start making, C and D. Now, that forward reaction is going to slow down as time proceeds because A and B are getting used up, their concentration's going down, so that forward reaction is going to slow down. As C and D build up, they can bump into each other and turn back into A and B. And as you get more and more C and D, this reverse reaction starts to happen faster. So the forward, that one's slowing down, this one's speeding up, and you hit a point where the forward and the reverse are happening at exactly the same rate. And at that point, it looks like the reaction has stopped, but it really hasn't. You actually have then A and B turning into C and D turning into A and B, but because it's happening at the same rate, you don't notice any net change in the amount of C and D compared to A and B. So this phenomenon was first, noticed in the 1800s by these scientists who noticed that if you hold the temperature steady, because changing the temperature, and we're going to learn that a little bit later, can affect the ratio of C and D to A and B. But if you hold the temperature steady, a chemical system of reactants and products are going to reach a state where the ratio of product to reactant has a constant value. And that value is called the equilibrium constant, and we use KEQ. Sometimes they use KC to represent it. What we're going to learn to do today is to write the expression, like the ratio of products to reactants, and then use the expression and some data to actually calculate KEQ values. So how do you write the expression for an equilibrium? So let's say this is our reaction, and the little a, the little b, the little c, and the little d, those are the coefficients. The big A, the big B, the big C, the big D, those are like the reactants and the products formulas. So it's always the products over the reactants. So you have whatever the concentration of C, and we use brackets because the brackets mean the concentration of. And they found that it is raised to the power of its own coefficient. So if this is 1C, that's C to the first. If there's 2 moles of C as on the product side, then it's the concentration of C squared. If there was 3 moles of C, then it's the concentration of C cubed, and so on. That is multiplied by the concentration of D, I don't know where my little C went up there, raised to the power of its coefficient. If you have 3 products, you'd have a third one up here. If you have 4 products, you'd have a fourth one up there, etc. But we only have 2 products, and I lost my whole line there. So there's only going to be 2 things on the top. On the bottom, we have our reactants. the concentration of A raised to the power of its coefficient times the concentration of B raised to the power of its coefficient. And what they found, and this is known as the law, and remember, anytime something's a law, that means that there is proof, there's data to back it up. The law of chemical equilibria says that the ratio of the products to the reactants raised to the power of their own coefficients is going to reach a steady number, which is called the equilibrium constant. Okay, notice these are multiplied. This multiplication right in here, not adding them. You're multiplying them, and this is multiplication down here. Okay, that's just a common mistake that sometimes students make, and I think it's because there's a plus sign up here. They think there's a plus sign down there, but there's not. Okay, so first we're going to practice just like writing those expressions, and then we're going to practice actually, performing some calculations with those expressions. When you do calculations at equilibrium, it doesn't mean that there's half products, half reactants. We'll get into that a lot more when we, look at some very specific equilibria. But what it means is that the forward rate and the reverse rate are happening at the same rate. And sometimes that means that there's a lot more products than reactants at equilibrium. If there's a lot more products than reactants, that probably means that the forward reaction, had a smaller hill to get over on those potential energy diagrams, a little bit easier because we ended up with more products than reactants. And the K value then is going to be big. It's going to be bigger than 1. I've seen K values that are in the hundreds, okay? And then if the K value is less than 1, that means there's not a lot of products. That means that there's way more reactants. And that probably means that, the hill on the reverse reaction was smaller, so it was easier for the products to turn into reactants. And at equilibrium, you have a lot more reactants and very little products. And I've seen equilibrium, constants that are like 10 to the negative 10th, 10 to the negative 15th. And you'll see those too when we get into, doing the calculations. So just know that these values can be really big or really small, depending on, which is present in a larger amount, the products or the reactants at equilibrium. You do have reactions where it is pretty close to 50-50. Then you're going to end up with, KEQ values that are pretty close to 1. So if you have a really small, like K value, like, 1.2, you got about half and half at equilibrium. So if all of the reactants and the products are in the same physical state, okay, this is important, then it is called a homogeneous equilibrium, okay? And you write the expression by, just like I said, putting the products over the reactants. You start out with your, KEQ. I've got that up there. Hold on. Give me a second here. Okay. So give me a different color too. All right. See if this shows up. No. Bad. All right. Hold on. So, oops. All righty. I guess we'll stick with the blue. Maybe give us some black. See how that shows up. All right. So there we go. That's good. So the KEQ is going to be equal to the products over the reactants. So on the product side, we have NO2, and you put it in brackets because the brackets mean the concentration of. And then since there's a coefficient of 2, whatever number you have there is squared. And then the N2O4 concentration, oopsie, sometimes it gets a little crazy. The N2O4 concentration is on the bottom, okay? And this is the expression that you would use to calculate a value for the KEQ. Try the next one. Give me a minute. You can write it down or think about what do you think it might be. And for this one, the KEQ value, you're going to have the CH4 times the water on the top. And they're both to the first power because they have coefficients of 1. On the bottom, it's going to be the carbon monoxide times the hydrogen cubed. So hopefully that's what you had arrived at. Now there's also something called a heterogeneous equilibrium. And that's where the reactants and products are in more than one physical state. Okay. Now, solids and pure liquids have an unchanging concentration. Like a solid, you always have the same number of atoms per unit volume because they have like set densities. Like for example, aluminum is 2.7 grams per milliliter. So like if you converted the grams to moles and you converted the milliliters to liters, you'd have a set number of particles per liter, a set number of moles per liter. So it's a constant, so it kind of gets lumped in with the other constant or the K value in the equation. Pure liquids also have set densities, and they can be affected by temperature. But remember, the law of chemical equilibrium said at a set temperature. So density is not going to change if the temperature doesn't change. And so these pure liquids like water is 1 gram per milliliter. You always have the same number of particles in every liter. So again, these two, the solids and the pure liquids, their concentrations, the number of particles per unit volume, doesn't really change. So they're not in the expression. They're actually lumped in with the K, the constant, because they are numbers that don't change. So when you see something like this, okay, and you've got more than one physical state, like here we have a solid, here we have a solid, okay, and here we have a gas. When you see something like this, the KEQ is just going to be equal to the carbon dioxide concentration here, okay? The solids are not included. So this would be, for example, if I had a container that contains some calcium carbonate, which is like a limestone, and I heated it up, it would only decompose until this concentration of carbon dioxide was reached inside of that container, and then it would quit decomposing. That's it. Well, it might be still going the two ways, but they're going at the same rate. So you wouldn't get any higher concentration of the CO2. This is kind of like in the last unit, we talked about how there's a maximum vapor pressure that can be reached inside of a container, of water. Now that's a physical change, but you can write a reversible reaction for it. Like if you have a bottle of water with a lid on, the liquid water is in equilibrium with the gaseous water. And the K value for that would only be equal to the gaseous water concentration. You hit a maximum value of vapor pressure at a certain concentration, and that's it. At that point, as fast as the liquid turns into the gas turns back into the liquid, and we don't see the water level in our water bottle going up and down. Okay, so solids, pure liquids, they're not included. Just gases, or the other thing that you can include is an aqueous solution, something that is AQ. Because if something's aqueous, that means like, if you look at this one at the bottom, that means like this copper nitrate is dissolved in water. And, that concentration could vary. You could have more or less copper nitrate, and that can affect, how many particles per liter. So that has to be included. So when you look at this first one, we're not going to include the carbon. So the KEQ is just going to be the carbon monoxide squared over the carbon dioxide. Try the next two. Maybe write them down on a piece of paper or talk them over with somebody that you're working with. Let's look at the second one. We're not going to include the zirconium. This is an I, zirconium iodide. Well, zirconium, yeah, I think that's iodide. An iodine over here. So the KEQ is going to be equal to the ZrI4 over, whoops, got myself got a little rogue line going there again. So over the iodine, which has to be, of course, squared. On the bottom one, you're not going to be including the silver or the copper as solids. So it would just be the concentration of the copper nitrate over the silver nitrate squared. All right. So now that you know how to write the expression, you can actually put some data in that can allow you to calculate a value then for the KEQ. So whenever you have a reversible reaction, first you have to write the expression, then you can plug in the numbers. We see here this is going to depend on the nitrogen times the rogue line again. Somehow I just keep getting that. The hydrogen cubed. And then on the bottom, we're going to have the ammonia, and that's going to be squared. Everything's included because this is a homogeneous equilibria. They are all gases, so everything's included. Now, in this data chart, we have the concentrations at equilibrium. A future lesson is going to help us learn how to get these numbers if we're not given them. But at this point, in this particular problem, we're given these numbers, so we can just plug them in and calculate an answer. So we have 0.533 times 1.600. Just cannot get away from that. This gets cubed because of 3 in front of the hydrogen. And on the bottom, we have 0.933, and that gets squared. So you'd have to plug that into your calculator. I did that previously, and I came up with 2.51, and that is the value of the KEQ for this reaction at whatever temperature this was being run. If the temperature is higher or lower, that could affect this value, okay? So this data is for a specific temperature, although that temperature is not quoted here. Now, hopefully, you will be able to take what you see in this video and apply it to the homework, where you've got these expressions that you write and then putting numbers in and calculating a KEQ value. Now, one thing that I do think is worth mentioning, and not able to write on the other one, but it is possible, let's say you have something that's a gas. Let's say you have something that's a gas. I don't know why I've gotten out of this mode where I can write on it. Here we go. Let's say you have something that's a gas before the arrow, and then after the arrow, you've got, a solid, okay? So when you go to write the K, the only thing after the arrow is, solid or liquid. If there's nothing up there, you just put a 1. And then on the bottom, you would put the concentration of your gas and, raise it to the power of whatever coefficient it was. It is possible to have a KEQ value that's 1 over something if everything after the arrow on the product side is a solid or a pure liquid. On the top, you can put a 1. Okay, so hopefully that helps. And, you're going to do some practice with this on homework and then use this skill in a lot of future lessons. So, all right, good luck with this. Thanks.